Okay, Assalamualaikum and good morning. So, welcome back to the lectures again. Let me just begin if, with something about your test one. Perhaps I see some tendencies of answering answering the questions using the solutions almost directly. So I think I should explain that being an open book exam, uh, normally the questions given to you will be slightly different from the assignment. So in other words, if you essentially copy directly from the assignment solutions, uh, you probably don't get your full marks. So I hope you understand. Probably, and most of you do not get what you call marks near to 15%, but essentially it's because of the solutions that you give is not quite precisely the ones wanted by the question itself. Okay, so do expect from the second test onwards. Okay, I may give you certain questions from the assignment, but I will change it a little bit. Okay, so in other words, it cannot be just an identical copy of the questions from assignment. Okay, so I hope everyone understands that. So maybe in the second test, you might get a better mark. Okay. So the other thing that I want to mention is that just before we left for the semester break, uh, we had a lecture that I sort of finished halfway because I wasn't happy with the lecture itself. So today we're going to repeat those, okay, and then hopefully it goes well today. Okay, so let me go to the lecture notes. So can you see this? Okay, great. So I think the one we have started from the lecture that sort of went halfway is, I think we started off with this idea of relativistic kinetic energy. So I will repeat this again so that it becomes recorded, and then you can actually look at it again later in the semester. Okay. So let me begin by trying to identify the idea of relativistic kinetic energy by looking at the idea of work done in the Newtonian context. Normally what we did was to just simply say take the force multiplied by the displacement, and your force in this particular case, because the examples that you probably have seen is essentially that this force is taken as constant. So it doesn't matter along the path, along the displacement path, it doesn't really depend on the coordinates of the path. But we're going to, we know that we can actually generalize this by taking your force to be dependent on your. So in other words, what we will do is to make your force as a function of x, for example. And what we're going to do, since it varies with respect to x, so then one has to be careful of how you contract with this displacement. So you normally just consider the infinitesimal displacement. So in other words, what you will get in this particular case, we'll get infinitesimal work done. Okay, so you get this as an analog for the simpler version of that. So this is for the case when your force is actually dependent on the coordinates of the displacement path. Okay, so right. So in other words, if you want to work out the work done in general, So you have to integrate this with respect to x from some initial point here to a final point. Okay. So the next thing that we want to see is to understand what this force is going to be. Okay, and the general case expression of the force is going to be given by F equals to dp dt. Okay, because I think we have already mentioned before that this will generalize your F equals to ma, because your m could also be changing along the way. Okay, and we have already done your P for the context of special relativity is given by mv over square root of 1 minus v squared on c squared. Okay, here your m here is essentially your rest mass, and previously I denote rest mass by m naught, but no, I don't want to keep doing that, so I'll be just replacing this by m. It should be understood in contextually when your m appears with the relativistic factor, then it's really representing the rest mass. Okay. If I do want to differentiate between the relativistic mass and the rest mass, then no, it will again depend on the context. Then there I will actually use the m naught rather than m. So here m here is your rest mass. Okay. So let's integrate this, and what else am I going to say? Yeah, okay. The other thing is when you differentiate this with respect to time, you have to remember that your v here depends on time, and as well the v inside your square root over here. So essentially you do all the necessary chain rule, and then you should be able to get this. Okay. So you plug this in into your work done expression, and then you use the fact that one can change. Here is an integral with respect to x. We would like to change this to an integral with respect to v, because your expression inside your work done is in terms of v. So what we're going to do is to denote, for example, just see, I think I've done this. Okay. So essentially what we do is to consider dx to be given by dx dt times dt, and this multiplies with dv dt. Okay, so that means what happens over there with when you multiply dv dt, so semicolon there, times dt. Okay, that can be re-expressed as dv. Okay, so the whole thing together now becomes v dv. Okay, so this will be dv dt times dx gives you v dv. And to make sure that we want to have the final expression to be dependent on v, so we change the integration variable from v to v dash. Okay, so this is just to make it to be different from the final expression. And once we change also the integral with respect to x to v, we have also to change the integral limits. So in other words, we have to look at what's the velocity at the beginning and what's the velocity at the final. So we'll take the velocity at the beginning as to be 0. So in other words, we're thinking of the particle being initially at rest, and then at some final point it will have some velocity v. Okay? So when you integrate this, then you have a final expression that depends on v. So the next thing that we want to see is essentially that this whole expression under the integral can be written in terms of this differential. Okay, so when you take the differential of this, so essentially what you get minus 2 dv on c squared. So in order for us to get back your dv dash over here, so I should be writing a dash here. There are a couple of mistakes, but you should be able to detect this. So so when you take the differential, you had this extra factor, so you have to multiply with the inverse outside, so that back to the same expression as the one before. Let me just check if everyone is okay coming in. Where are we? Yeah. So now what we can do, since this is now in terms of this differential, we can re-express it as some other variable, say variable s. Okay, so we'll have it as the variable s. Oh, the other thing I've shown, this is again another mistake. Here when we do the integral, your limits change from x to v. So we have this 0 as your initial velocity and v as your final velocity. Here again, you are differentiating with respect to a different variable. So this is actually wrong. It's the wrong thing. I should be looking at what actually happens for this expression at v equals 0. So if you look when v equals 0, okay, so that would be 0 squared on c squared. That gives you 1. And that explains the 1 over here. And then when v equals to v, okay, sorry, v dash equals to v, then you get 1 minus v squared on c squared. So this limits here should be these limits. Okay, so you integrate this, you substitute this just like a different variable s. So this is ds over here, and then this is s to the power 3 over 2. And essentially that's an easy integral for you to do. Here I'm just flipping because you have the minus sign here, so I flip the integral, so your upper limit becomes the lower limit here, and then your lower limit becomes the upper limit. Okay, and then you just simply integrate this. You know how to integrate this easily, so you get this factor coming out. Okay, and then you take the limits between this is again wrong, this is actually 1. Okay, please make the corrections later on. Okay. Okay, so you just substitute the limits into the integrated form, and you'll find that your work done is given by this. And it's a good thing to have your work done being expressed in terms of a difference between two quantities. Okay, in fact, this will establish what we call the work energy theorem. And we have done classical mechanics before, that your work done is essentially the change in kinetic energy. Okay, so the change in kinetic energy, I'm going to write, by right, I should be writing this to be delta T here. So here, delta T is now, I'm rewriting this as T, so that no, I don't have to write this delta all the time. Okay, so this what you call difference in energy here is given by this difference between the two expression here, and here essentially is just the factor gamma. Okay. It's gamma, so you can re-express this as gamma minus 1 times mc squared. And do remember that this is essentially your this is your rest mass, so this will be your rest mass energy. So Okay, that's great. Let's see what this actually corresponds to the limit when your V is much less than C. Then you'll find that essentially that this difference between these two energies, okay, just gives you your kinetic energy. Okay, this is just using your Taylor series for this square root in the denominator. Okay, so and then what we're going to do is to invert this formula to get an expression in terms of your expression for V in terms of your kinetic energy. So you just rearrange this equation, okay, and then I'll be able to write this. Now, why we want to do this? Now, if you remember for classical mechanics, or Newtonian mechanics, rather, right, Newtonian mechanics, your T is given by half mv squared. So in other words, what we have over here, your V is equals to 2T over m. Okay, so we can actually make the comparison later on when you look at the relativistic expression compared with the case of your Newtonian expression. Okay, so if you plot those, so this one you can actually see that this is going to be a parabola. Okay, so this parabola, when you plot t in terms of v, this gives you this parabola. But when you plot v, so let me just write the v and t here. So if you plot v in terms of t, then you get this kind of parabola. Okay, so so here when you do the plot, so here you get your parabola for your Newtonian case. Okay, but for the case of your relativistic case, you'll see that it gives you a different curve which sort of flattens as you go higher in velocity. Oh, sorry, higher in energy. Sorry, okay. Higher in energy. So your velocity is flattens off to 1 here. So here your asymptote here is essentially 1. We are expressing this in terms of units of C. So in other words, V equals to 1, V over C equals to 1 is just V equals to C. Okay, so you will never get beyond the value of C. Okay, and if you try to take the limit of V goes to C, then essentially your energy that you need to do so will require an infinite amount of kinetic energy, which of course usually realistically you don't have that. Okay, so the final thing is essentially to re-express this equation earlier. Where is it? Yeah, this expression over here to give what we call the total energy. Okay, so remember that T equals to gamma minus 1 mc squared. Okay, so what I'm going to do is to write this. I'm going to bring this mc squared on the other side. So I'll get T plus mc squared, and I define this as your total energy. Okay, so that is the expression that you get from analyzing your expression for work done. Okay, so that sort of finishes off this particular lecture 10. So let me move to the lecture 11, which is also problematic last time because one of the things I noticed, there are some mistakes, so I'm going to highlight these mistakes, and then you please do the correction yourself, okay? And when you look at those notes, okay? So here's lecture 11. Okay, so the idea of lecture 11 is to look at the case of motion and spatial relativity that correspond to the idea of motion with constant acceleration. So if you do for the case of Newtonian mechanics, okay, just give you some motivation why we want to do this. You have the kinematic relation for constant acceleration. That you have always seen is v equals to u plus at, and then s equals to ut plus half at squared. So we're going to see all this expression in the relativistic form. Okay. Of course, when you do special relativity, when you try to transform this to the relativistic expression, then you find that some changes will be there. Particularly if you look at how this equation looks like, okay, you'll see that definitely there's going to be something wrong, because when you take t goes to infinity, then your v can goes to infinity as well. Okay, so and this is not possible in special relativity. Okay, so we're going to see how we do this. Like before, we need to redefine what we mean by constant acceleration. Over here, the convenient thing that we can actually do is to go to the proper frame of the particle. Okay, so in the proper frame of the particle, you remember that your instantaneous in proper frame, your instantaneous velocity. I think I denote this by u. Okay, will be equal to 0. Okay, so but that doesn't mean that it's constant. Okay, it's just at that particular moment you have your u to be equal to 0, but as you know, let time evolves, it will change the velocity, but then you you change your frame. Okay, you change your frame to a different frame, which is again having this instantaneous velocity to be equal to 0. So that's the idea of proper frame. Okay, so it's the frame is actually moving together along with the particle. Okay, but having that, as I said, given your instantaneous velocity to be 0 doesn't mean that your velocity doesn't change. So what we claim instead is that your velocity will change in accordance with the idea of constant acceleration. Okay, so in other words, the proper acceleration is actually constant. So this will replace the constant acceleration that you have in Newtonian mechanics. So let's do this and see what we get. So what we're going to do is to consider two different frames. One is some normal frame where you see the particle moving with certain velocity. Okay, so here is in frame K, for example, this velocity of the particle is going to be u. Okay, but in the other frame, so you can think of your K dash frame, but your K dash frame, we can take it to be your co-moving frame, the proper frame. Okay, so instantaneously that your u dash will be equal to 0, but your derivative of u dash is going to be equals to a. Okay, and to make it simpler, we will set it to be a one-dimensional motion, so everything is actually moves in the x direction, so that you can just do the integration much more easily. Okay. So here is probably where I had little problem before. The idea of transformation law for acceleration, I have not actually introduced this properly. Okay. So essentially, that's another reason that you probably will not be able to see this. I think in the previous semesters I set this as an assignment question. Okay, but for some reason I've forgotten this. Okay, in previous semesters. So the idea is again is like doing the when you derive the formula for addition of velocities. Okay, so you should be able to get some kind of formula for your velocity addition. If you want to have some details of this, you can look at the book by Faraoni. See, I have it here. Okay, just refer to Faraoni. I think this would be somewhere in the earlier chapters. Okay, probably I think chapter 2 or 3, I'm not sure. Okay. So you can see, in fact, in the Faraoni's book, it considered a three-dimensional case. So there will be in one dimension, in one of the dimension, it has this what you call, the frame is considered to be moving. In the other dimension, is considered to be not moving. Okay, but then you find that there's your acceleration components will change differently for the orthogonal case and for the case of your where it's actually moving along that particular direction. So here it's actually doing it for the case of one dimension, so there's only one component. So it's given by this transformation law, and you can actually see this inside this book. What I'm going to do instead, since I have not touched this before, I'm going to refer back to lecture 10. Let me just see where it is. Lecture 10. Sorry, got to find it. Where's the point? Yeah. So what we can do instead, we're going to use this formula. Okay, and maybe I'll go to the whiteboard here. So what we're going to do is now we use that formula. Let me write it down here. dp dt equals to m divided by 1 minus v squared on c squared, 3 over 2, and then dv dt. Okay, so we're going to use this instead to derive the transformation law for the acceleration. So what we'll do here, we'll remember your v in the previous case was the velocity of particle. So what we're going to use then over here, we use u equals to v, because in this one, for example, we are using why we're changing the notation here. So it's quite confusing, but I hope you bear with the changes in notation. So where are we? white one. Yeah. So you use u equals to v, and then you use u dash equals to p over m. Okay, so this would be the one sort of going in the proper frame. Okay, so then you will see that, okay, you'll find that the u dash, the t dash, okay, there's a bit of assumption, but no, I think you can see the analogy from the previous equation. So this will be 1 minus u squared c squared 3 over 2, and then this will be du dt. Okay. Remember that this is in the proper frame. Okay, so this is in the proper frame, and in the proper frame, this velocity, well, the velocity is instantaneously zero, because you know your proper frame sort of follows along the particle, so your particle seems to be at rest, but essentially this the derivative is essentially correspond to your what we call the proper acceleration, and that proper acceleration over here is now constant. Okay, so in other words, what we will have, so we A equals to 1, is it, there's some lag here, u squared on c squared 3 over 2, oh come on, sorry about this, it's this, oh dear. Are you still seeing this?
Black screen. Black.
Now it's back? Can you see it now? Yeah, I'm having problems. Okay, I'm having problem with my tablet. Yeah. Let me see. Okay, should be back. So that 3 over 2, and this is your in this particular case is your du dt, and then you can bring this on the other side. Okay, that gives you du dt equals to 1 minus u squared on c squared 3 over 2 a, which I believe is the expression in the notes. Okay, one could also use this. Then what happens in this particular case, then essentially your v going to be equal to 0. Okay, because it's the instantaneous velocity, and then your gamma cube will just 1 minus u squared on c squared. So it gives you the same expression. Okay. So now what we're going to do is try to integrate this, because this is your sort of acceleration in the other frame. Okay. So what we want to do is to integrate this. Okay. And for this, we are going to use this particular identity. Okay, you can look this up, or you can try to prove it. And what we're going to do in order for this to be looking like this integral, so I'm just going to rewrite this as follows. So I will have, if you look at this, okay, let me rewrite this over here, du over 1 minus u squared on c squared 3 over 2. I can put everything in the denominator over here as follows. So I have c squared minus u squared c squared 3 over 2, and this is now it should go on top. Okay, And remember that this is c squared to the power 3 over 2, so that will give you c cubed. Okay. So now it really looks like this because you have your constant a squared here is given by your c squared, okay, and then your zeta here, I think, let me check. Okay, your zeta is actually your u squared. Okay, so here you just use a equals to c and zeta equals to u. Okay, so you just plug substitute this into the answer for the integral, and then you should be able to get this. Okay. So the next thing, remember that this is an expression after the integrals where you actually use it's actually a sloppy kind of notation here. I'm using the same u that you have in your final answer with the integration variable u in this integral. I should be really writing this instead, u dash here. So then when you put in your limits, I can make it into something which is dependent on u instead of no. If I do this, essentially no, the u will be disappearing over here. So that's why I need to replace it by a different integration variable. So sometimes no, this is something that often I do it in one shot, no, without really thinking about all these final details. Okay, so here is your u dash integrated, okay, coming from here, okay, integrated with the limits now been taken from some initial velocity to a final velocity, and for our convenience, we're going to take your initial velocity to be equal to 0. Then I will get this instead, okay, and this is expressed in terms of this. Okay, remember that we are doing the integral with respect to t here. Okay, so you need to integrate with respect to t, and then you will get t minus t naught on the other side. Okay, re-express this thing, everything over here, then you get this expression u squared, and one can multiply. You remember here you have u squared, but you also have u squared on this side, so you bring together the terms with u squared. So I'm going to have this, and what's left will be this term multiplied by 1, and that gives you that. Okay, so now I can bring this on the other side and then take the square root, then I will have now an expression for the final velocity. Okay, so this is a bit confusing. Your u earlier in the Newtonian case of the initial velocity, but your u here is the final velocity, because what we did was u naught is your initial velocity for this particular case. Okay, and we have taken this to be equal to 0. Okay, so this is really your final velocity. Okay, so no, please be aware of this notational changes. So now we can actually compare this with our Newtonian case. Again, no, you'll see this different notation again. V equals to u plus at, or if I want to, I can rewrite it in the similar notation will be u naught plus at, but u naught is 0, so you can see that u is going to be equals to at in the Newtonian case, but here you'll find that your u is given by some complicated function of t, okay, because you also have this denominator with the square root. Okay, so that sort of replace your familiar kinematic formula for Newtonian mechanics, we have another one for the displacement, right? So we'll do another integration for this. So this should be compared with s equals to ut plus half at squared. Okay, or in this case, in the right notation over here, it should be u naught t plus half at squared. Okay, so let's see how we do this integral. So you have this expression now coming from the earlier expression for u. We can make this simpler by some substitution of your variable here. So I define this to be your xi dash. Okay, so over here it's almost xi dash without that c squared. So I'm going to have to multiply this with the c squared on a over here, on the other side. Okay, so I have this integral now, xi dash divided by square root 1 plus xi dash square. Again, I'm going to do this another substitution so that your d xi dash can be now be written in terms of d of 1 plus xi dash squared, and again there will be some difference in factor. So the difference factor over here is a factor of 2, so I'll multiply this by a half. Okay, and the other thing that I think there was another mistake here. The other thing is the limits. Okay, here the limits is for t over here. Here is the limits for your xi, and okay, this has already been replaced. But moving from xi dash to 1 plus xi dash squared, then you have to replace this again. Okay, for 1 plus xi dash squared, when xi dash is actually equal to 0, then this will become a 1. Okay, and for the upper limit will be this 1 plus at minus t naught over c squared. Okay, for the upper limit. So okay, this is the mistake. So this, if you write this as s, okay, so this will be what? Integral of s minus a half yes. So what's the answer? It's not going to be s, of course. So in other words, this is actually should be s to the power of half. Okay, so please make the correction here. This is actually s to the half. Okay, so s to the half evaluated at 1 and 1 plus at minus t naught over c squared will give you this quantity. Okay, and you can re-express it in this way if you want to. But the more important thing is to rearrange it in this particular form where you bring out all the expression for here. I'm just bringing this term on the other side, okay, and then leaving this square root term on the right hand side, and then I can get rid of the square root, so I'll be able to write a square for this, and then here the square root is gone, and I'll find that okay, I can rewrite this everything in terms of an equation which is the form of the hyperbola. Okay, so in other words, by setting the right initial condition over here, so we take t naught equals 0 and x naught to be equals to c squared on a, so that this cancels out, and I'll be able to get your standard form for your hyperbola. Okay, so in other words, Oh, I should mention earlier. So this one will be the analog of this ut plus half at squared. Okay, so this is the equation. But now you are actually re-expressing this as a curve which is having both x and t inside a particular equation, for which you can rewrite it if you parameterize your t as a function of another parameter and your x as a function of parameter, so that this equation is actually being satisfied. You can do this with your hyperbolic sine function and a hyperbolic cos function. Okay, so in other words, we substitute this, then essentially this will give you this particular equation, and this is essentially the thing that we had earlier. I think as a toy example that we had earlier, okay, of an accelerated motion. Okay, so that sort of finished this part. So now let me go to this part. I have another 10 more minutes. Let me see. Let me finish this. Okay, and then we can go back to new things. So so we have seen the hyperbola is essentially it's the case of the motion of a particle undergoing constant acceleration and special relativity. Okay, so if we try to plot the hyperbola, for example, over here, so here's essentially is a particle which is undergoing constant acceleration. Okay, here is the essentially the what you call the line that gives you the light cones. So t equals to x over here. So another one is t equals to minus x over here. Okay, and you can see that your t equals to x and t equals to minus x is the asymptote of this hyperbola. Now, what's really important over here, you'll see that, okay, if I'm not inside this shaded region, so for example, I'm here, I can send a signal to this accelerated observer. Okay, I can send a signal, and let's say I'm going to use light itself, so I can draw a parallel line to this line. So let's over here draw a parallel line. I can essentially communicate with this accelerated observer. Okay, but once I'm inside this shaded region, or even at this boundary here, I won't be able to what you call send a signal to this observer. Okay, so if I do, for example, over here, see, in order for me to send a signal that reaches the observer, then I will have to draw a line in this way. But this line is having a what was it? The slope is less than the slope that you need for, okay, the inverse slope is actually gives you the velocity. So this is a velocity which is greater than c. So this is actually, this signal is a signal with this v greater than c, which no, you don't really have that unless you have a hypothetical particle called tachyon. But so in other words, this kind of signaling is actually prohibited. Okay, so the only way, if you want to send signals, it has to be not inside this shaded region. Okay, so you can send signals here, you can send signals here, or even near this border, I can still send a light signal to reach the observer at this particular point. somewhere in the future there. Okay, so in other words, this horizon, this boundary is what we call a Rindler horizon. Okay, so which uh, it's like your event horizon for your black hole. So once you're inside the black hole, okay, you cannot send a signal outside the region of the black hole. Okay, and the precise boundary essentially is called the event horizon in the case of the black hole. Here we are not talking about black holes at all because we are not considering gravity here. Okay, right. What else? Let me just finish this off if you don't mind. So the other thing that so I can think of an observer here accelerating in this manner, and the accelerated observer will actually feel no they can feel changes with respect to what an inertial observer see. An inertial observer will always see a vacuum, for example. Where is it? An inertial observer, a non-accelerating observer here, will always see a cold vacuum. Now, for an accelerated observer, what's going to happen to the observer itself, which is accelerating? It feels some energy, okay, because to him he's at rest, but the rest of the universe is actually accelerating towards him, okay. So he feels that energy, and that energy is given is interpreted as what we call a thermal radiation, okay. And this thermal radiation has a temperature which depends on the acceleration of the observer itself. Okay, so this is what we call the Unruh effect. I'll be giving you an SEL module. Okay, immediately after this, I guess. I will upload this on Putra Blast, and one of the papers will actually discuss Unruh effect. Okay, so later I'll explain about the SEL module. Okay, the idea of an Unruh effect is actually still being debated because it's not easy to do experiments for this particular effect. But what instead people actually know is that you do have accelerating particles. Okay, you as an observer, you can actually see a particle accelerating, but to see yourself accelerating and see what actually happens is a different story. Okay, so for the case of accelerating particles, an observer outside the accelerator will be able to see that okay, the particles will actually obey E equals to gamma m naught squared, so m naught c squared. I'm using m naught back. Okay, gamma m squeezed c squared. So let me just rewrite this so that okay. And I can now invert this to give the gamma, which is your relativistic factor, to be equal to E over mc squared. Okay, so if you fix E and let your m changes, and then you can see that your m changes will make your gamma changes. So for example, if I have a bigger mass, then your gamma here, your relativistic factor is going to decrease, or I have a lighter mass, then your relativistic factor is going to increase. What does it mean by this? Let me just make this a bit clearer. Let me go to the whiteboard instead. Clear this up. I hope you don't mind me going slightly beyond. Do you have a lecture after this? Anyone? Okay, in that particular case, then I will probably stop at this point, and I'll continue the next lecture. Okay, so let me take the attendance here. Sorry. Okay, I'll continue this lecture tomorrow. Okay. Okay, thank you everyone.